Hi there, my name is Microstructure, and today I'm going to be talking about crystalline structures. So, what are crystalline structures? By definition, crystalline structures are structures that have their atoms arranged in an orderly and predictable way. Crystalline structures are known as anisotropic, which means they respond differently to forces depending on the direction of impact that the force hits them at. The opposite of a crystalline structure is an amorphous structure, and so amorphous structures are known as isotropic, which means they respond the same way no matter what the direction of impact is. When compared to amorphous structures, crystalline structures are also generally more brittle, and they can break easier. Since all the bonds of a crystalline structure are the same length, they are all equally strong. This means that all of the bonds in a crystalline structure can be broken by the same amount of energy, and this in turn means that the melting points of crystalline structures are very, very specific, which is opposed to the broad range of melting points that can be found in amorphous structures. Crystalline solids typically form in a structure known as a closest packing arrangement, which allows the substance to fit in as much atomic volume as possible in as little space as possible. And this concept is known as efficiency. So, crystalline structures can be found in a number of shapes, specifically 7. These shapes are in the picture on the right, and they are simple cubic, tetragonal, orthohombic, hexagonal, rhombohedral, monoclinic, and triclinic. Each one of these shapes has a distinct number of categories that make it that are specific to that shape, and additionally they have mathematical equations that go along with each shape that can predict the exact dimensions and properties as well. Additionally, aside from shapes, crystalline structures have 3 different subcategories. These include molecular crystalline structures, ionic crystalline structures, and atomic crystalline structures. These categories are based on composition as opposed to shape. So molecular solids are made of covalent compounds, and they form an orderly crystalline structure as they solidify, while their molecules, they remain unchanged. So some examples of molecular solids might be water, or ice, or dry ice, or sugar, or any kinds of sugars. Ionic solids are made of ionic compounds, and they are highly soluble and have very high melting points. So salt, for example, is an ionic crystalline structure. Atomic solids are made of individual atoms as opposed to molecules like the other 2 subcategories. So within atomic structures, there are 3 different subcategories, which include network atomic crystalline solids, group 18 atomic crystalline solids, and metals. Network solids have an extremely rigid crystal structure. These are kind of known as the larger molecules in the crystal world. And an example of a network atomic structure is the diamond. Group 18 solids are the solid version of the noble gases. So group 18 on the periodic table, which is where the name comes from. So noble gases with their full valence shell have very little interest in interacting with both other atoms and themselves, which makes it very, very difficult to cool and pressurize these gases long enough to become a liquid, and even more difficult to make them become a solid. Upon solidification, group 18 solids are held together by weak and very, very unstable van der Waals forces, so they therefore do not stay solid for long. For this reason, group 18 solids are extremely rare and difficult to find. Metals are considered crystalline structures because their atoms are arranged in a variety of orderly and predictable ways. There are a multitude of arrangements that the metals follow, which corresponds to the closest packing arrangements I mentioned earlier, and it's essential for packing the metal atoms together in the most efficient way possible. Despite the closest packing arrangements, most metals are very malleable and ductile. And this is because the atoms and the bonds between them are arranged in a certain way that allows metals to be both compact and malleable and ductile. Additionally, the atoms in metal, the metal atoms themselves are very, very large, which prevents valence electrons from being held tightly to the nucleus. And so this is why the electrons in metals are allowed to move around more freely than electrons on most other elements. And so instead of like a normal element might contain its own electrons, the electrons in metals are allowed to move throughout the whole substance in a sort of sea of electrons, where the electrons can travel from one atom or one nucleus to another. And so because of this, this is what makes metals able to conduct heat and conduct electricity so well, and gives it those unique properties. The crystalline structure of metals is extremely strong, which makes what makes metals so durable, because the metal atoms are tightly bonded to their surrounding electrons while they are moving around. However, these metal atoms are uniquely flexible, which allows the metals to undergo the properties that are specific to metals, for example, malleability and ductility. So for a comparison model, I'm going to be kind of describing closest packing arrangements, and I'm going to do this by comparing individual atoms to tennis balls and trying to fit these tennis balls within a box. So for simple cubic packing, the first of the three closest packing arrangements, it could be compared to stacking the balls directly on top of each other. And so this means that each ball touches exactly 6 other balls. So each atom touches exactly 6 other atoms. So in the picture on the top left, that is a picture of what simple cubic packing looks like. Keep in mind that while these show individual units of the balls, it is not analogous to the number of atoms that are in a closest packing arrangement. For example, here we can see that there are 8 whole tennis balls in the picture on the top left. However, in simple cubic packing, each unit cell, which is what one unit is called, each unit cell contains exactly 1 atom's worth of atomic volume. So for body-centered, and additionally, simple cubic packing allows for a 52% efficiency, which means that about 52% of all the space in the substance is actually comprised of atomic substance. For body-centered cubic packing, it can be compared to placing 1 tennis ball in the empty space created by 4 other balls in a lower layer. This is shown in the bottom left picture. So as you can see, there is 1 ball in the center with 4 balls below it and 4 balls above it. So in basic cubic, body-centered cubic packing, each atom or each ball touches exactly 8 other atoms or 8 other balls. The name body-centered cubic comes from the fact that there's a center body, center atom, and the 8 other atoms around it form a cube around this center atom. The result after adding this all together is the picture that you see in the bottom left, and this allows a 68% efficiency for closest packing arrangements. Finally, the most efficient packing arrangement is face-centered cubic packing, and this is analogous to packing the tennis balls in a sort of triangular shape, where you place each tennis ball in the empty space created by 3 tennis balls in the layer below it, as opposed to 4 in body-centered cubic packing. So as you can see at the picture on the right, the kind of triangular shapes fit into that hexagon in the middle, and each ball touches exactly 3 other balls in the layer below and above it. In the layer below it. This means that since they are in a triangular shape, each atom will touch exactly 12 other atoms, or in this diagram, each ball touches exactly 12 other balls. And so the results of multiple layers of this is shown on the very far right-hand side with the multiple layers. So why is this important? Knowing how to identify and classify crystalline structures within materials can help a researcher, create a number of research guidelines, which mainly pertains to safety and the actual experimental design, experimental process. For example, if I were to be doing a research project and beforehand I knew that one of the substances I would be working with was actually a crystalline structure, a crystalline solid, I would already know multiple things about my experiment and the substance itself. For example, I would know the substance would have a very specific melting point, and it might be broken by the same amount of energy. So therefore, I might not want to test those things because they're things that are already known and might not be very interesting. Additionally, I would also know that the substance would be anisotropic, so I could design an experiment around how the substance reacts according to which way I impact and I apply force to the substance. Additionally, knowing the categories of your material is important as well. So if I knew exactly what categories my substance fell into, I might know a variety of other properties. So, for example, if I knew that I would be working with a group 18 atomic crystalline structure, I might take precautions around the fact that the substance is extremely unstable. Additionally, I would try my best to conserve the substance because group 18 atomic solids are extremely rare, and so I probably would not have an abundance of the material. Additionally, I might also consider that I should only conduct the experiment within a very condensed and brief amount of time, seeing as how group 18 solids are extremely unstable and they don't actually stay as solids for a very long period of time. So that is it, and I hope you enjoyed my presentation. Thank you for listening.